All right, so while we wait for people to come in at the end, listen, I'm going to try to run through. So if you were the person who came to my office and asked these questions, sorry you have to hear it again. But I've had some questions from several of you about registration. There are several sections of Orgo 2 in the fall, but fewer than Orgo 1. You can take just some business stuff that you can take you can take 223 lecture, but not the lab. Like you don't have to have the two at the same time. You can't take the lab first. There's no real reason to do that. Like it doesn't buy you anything. So I strongly recommend that you take the lecture and the lab at the same time, unless like next fall's schedule is going to be a little wonky. So if it just works out, like the only lab you can get into is an evening lab. I actually don't know the 223 schedule. I'm not in on it. Like if you have a whole bunch of morning classes and the only lab is a night lab and you don't want to be in class 14 hours in the day, you could split them up. This is going on recording, all right? So the two professors teaching 223 are both very good. They're good friends of mine. I'm not going to tell you which one's better or worse. I will tell you they're both highly qualified, very competent. I would let it come down to your schedule, right? Same thing. If given the span of time the classes will be offered next semester, I think you guys would be well within your rights to try to put everything in the morning or everything in the afternoon, right? The real worry is you're going to have an 8 a.m. class and then a 7 p.m. class. Let's see, what else? The final exam is, quote, optional. So if you've taken all 3 midterms, go ahead, sit down. So if you've taken all 3 midterms, you can use your average on those 3 for the final exam. All right, so let's say you've done 3 85s. Your midterm average is 85. You can just have an 85 on the final without taking it. It is totally up to you. If you show up and start the final counts. All right, so if you show up and halfway through you're like, oh my God, I didn't learn anything and I don't know any of this, you can't leave. Yes? You will have your exam 3 grade. Yeah, it might be Friday, okay? The final is on Saturday. I will get them graded as fast as I can. So my hope is to give them back to you on Thursday in class. Or I guess I've been emailing them. But you'll have that score, and I'm happy to talk to anybody. Like I think it's pretty clear, if you're under 80, probably you want to, roll the dice and take the final. If you're in the 90s, you probably don't. The final exam, there's not a lot of time to study for it. Third exam is May 4th. The final is May 8th. The idea is the final exam's cumulative, roughly a third from each of the 3 midterm tests. And you just sort of roll in there with what you've actually learned. So it's not what you can study in the days leading up to it. It's what's actually stuck in your head. So in that respect, the final is tougher than the other hour exams. But I write the test knowing that, right? So my goal with the final is to see that you know the basics, and I will not be ashamed to send you on to Orgo 2. The best way to study for the final and get the curve in this class, there might be some curve at the end, but it's not going to be like an 82's an A. The best way to handle reviewing the old material is to work that final project. All right, so the final project's long. It's got a lot of the earlier stuff. It's open book, open note, open discussion. It's 150 points, which means it's as many points as the final. That one isn't optional. You can't just decide to take your homework score on that. So you have to turn that in. And honestly, if you start that early enough and approach it with some seriousness, you probably, you can score in the 140s pretty easy, which is a lot of points coming your way. You won't know that score, unfortunately. Like, that's not due until May 10th. And look, grading that is a grind. There's no way I'm getting that to you. Even if you turn it in early, I'm not going to, sit down and grade it special for you. Yep. I mean, you'd have to do the math, but it's right. I don't know. It's 150 points, which means it's an hour. It's worth one midterm and a half. It's worth as much as the final, right? How much would it help you to ace the final? Like, so if you make a 150 on the final project, it's going to add a lot of points to your grade. Yeah. Yeah, you'll have that. Yep. Let's see. What else? Anybody got any other kind of business questions before we start? It's gonna, like, my anticipation is I'm probably gonna give you guys all those points. The only way you wouldn't get the Wiley Plus points is if I turn it, if I go into Wiley Plus and you've never attempted anything. All right, if you've been working on it, I know I had some rule. My goal with that is to make you work problems and give you some reward for working problems. My goal is not to add a burden to your life, okay? So if you find and the Wiley Plus was probably more helpful earlier. It's better, it's not very good with mechanisms. It's better with drawing structures. It's really good for multiple choice and fill in the blank answers. There was another, did I see another hand? Yeah. If you're worried, you can come talk to me about that. But it's, like I said, my anticipation is giving you most of those points. And then don't worry about what Canvas says your grade is. Canvas doesn't have the rubric. It's just sort of adding stuff up. Your homework and quiz grade will be prorated Wiley Plus. Like, do I give, and it's not going to be your Wiley Plus percentage. It will be 15 out of 15 because you did Wiley Plus. Then your quiz scores and your homework scores, all of that is a percentage multiplied by what, it's like 100, 150, anybody? Yeah, whatever it says in the syllabus, multiplied by that. So you'll know that, you'll know your 3 exam scores. And so like I said, that's, there's 300 points in the final project and the final exam that will come after that. So there's a lot of points still on the board. Okay. Oh, crap, the thing I could have been doing. So if you were here last time, you got that flow chart. If you weren't, I hope you looked at it. The flow chart is on the back of this sheet. On the front are problems we're going to work. I don't know if we'll get to all of them or not. Probably not. Yeah. Go ahead and start at the top. I'll interrupt occasionally. You can talk to each other. You can ask me questions. I'll give you a few minutes, and then we'll do the first couple, and then we'll keep going from there. If you get extras at the end, pass them backwards. Sorry? Yeah. The answer's a lot, right? If you ace 150 points, it's going to really help your grade. So, but I don't. Yeah, here you go. I just don't know the exact number. Yeah. So you're going to want to use the flow chart to answer these questions. You can certainly look at the flow chart. Those of you at home, this will be on Canvas. How does that look? Oh, good, it froze. All right. That's the assignment we're working. By the way, you probably should know this. You use this in lab, so hopefully everybody knows this. DMF is dimethylformamide. Okay, so there's an amide there. Form is what you get when you have an H bonded to a carbonyl. So if H bonded to a carbonyl is bonded to another H, that's formaldehyde. If H bonded to a carbonyl is bonded to an OH, that's formic acid, et cetera. All right, so this is a very polar aprotic solvent. We'll talk more about solvents later. It also was the initials that my undergraduate advisor used for his graduate student. You can work that one out later. So obviously start with the top one. If you finish it and you have it, we're going to do them all. So go ahead and keep working the sheet. I'll interrupt you here in a minute. Okay, let me interrupt and do the first one. And then you can sort of evaluate if you're doing it right. You can just keep going. So, first question on the flow chart. This flow chart starts in the upper left-hand corner, not in the center. First question to ask yourself is if there is a leaving group present. Is there, in this reaction, a leaving group? All right. A lot of people are saying yes. What is the leaving group? Bromine. Is OH a leaving group in Chapter 7? OH is not a leaving group in Chapter 7, all right? I'm emphasizing Chapter 7. In Orgo 2, you'll see some cases where hydroxide does leave. Hydroxide can only leave under super basic conditions, all right? So in chapter 7, we never really have conditions like that. So for right now, just sort of memorize hydroxide, and anything that's as strong a base as hydroxide is not going to be a leaving group. All right, like I said, it's probably easiest, like the amount of leaving groups we have in chapter 7 aren't real long, so memorizing them is not super hard. Chloride, bromide, iodide, sulfonate, anions. That's it. Okay, so there is a leaving group. That means we can do chapter 7 chemistry. Now, are there beta hydrogens to the leaving group? How many beta hydrogens are there? There are 4, all right? So the alpha carbon is the carbon with the leaving group, 2 beta hydrogens there, 2 beta hydrogens there. So we can do elimination. We're going to be able to do elimination and substitution. Now, this is the sort of the center question, and this is the one I think that more often than not trips people up on these problems. Is there either a strong base or a good nucleophile present? Who thinks there is? Show me a hand. Who thinks there isn't? Nobody's willing to admit that there was a lot of no votes there. So this one really is either. All right, so you could have a good nucleophile that's not a strong base. You could have a strong base that's not a good nucleophile. The answer, if either of those cases is yes, you go to the left. If the answer would be no, you'd go to the right. So the answer here is yes. So what is the good nucleophile? Yeah, so the thiomethoxide. Okay, so again, if you see a sodium or a potassium or a magnesium or a calcium, that's going to be a plus whatever it normally would be. So this is a sodium +1. That means the SCH3 is going to be a minus. That means that S is a minus, right? So this is a sulfur anion. It's a really good nucleophile. It's a base. So a Lewis base, again, is an electron donor. It's something that's giving away electrons. So a Bronsted base that's grabbing a proton gives away electrons, and a nucleophile that makes a bond to carbon is giving away electrons. Sulfur is really good at giving away electrons to carbon. It's a little less good at giving away electrons to hydrogen. All right, that's a deeper subject. But this is a good nucleophile. It's not a super strong base, but it's a good nucleophile. And so the answer is yes. We're going to do either SN2 or E2. We're not really going to see much SN1. And again, this is not like a law of physics or something, all right? You can have a good nucleophile in SN1 or E1. It's just rare. So in this case, your mechanism is going to be SN2 or E2. So then, is the leaving group on a tertiary carbon? That's a question to you. Is the leaving group on a tertiary carbon? No, it is not. What kind of carbon is it on? It's on a secondary carbon. So alpha carbon, count how many carbons are off of it. 1, 2, that's a secondary bromide. So we can do SN2. If you see there going left, if this was a tertiary carbon, you cannot do SN2. SN2 does not happen on tertiary carbons. And so the best you're going to be able to do, probably it's going to be E2. In a protic solvent, you may get SN1 or E1. All right, so we said no. So then what's the pKa of the conjugate acid? And this one then is sort of, this gets, the farther you go in this flow chart, the fuzzier the answers get. Okay, the conjugate acid here is CH3SH, and the pKa is about 7 or so. Like I said, that's a reasonable base. It's not a super strong base, but it's a decent base. So then stronger base gives better elimination, can give better elimination. Really here we can do SN2 or E2. So it's right on that borderline. What's really going to decide this is going to be the temperature. I need a different color. Like I said, a pKa of 7 or 8, I honestly don't. I should have looked this up. This is probably 7 to 9. So the temperature is pretty much going to decide us between E2 and SN2. All right, so thiomethoxide is a decent enough base to do E2. It's a better nucleophile, so SN2 is going to be a little faster. So really, after everything, before you get to the temperature, we can do SN2 or E2. And so at that point, what determines the major product is going to be the temperature. Lower temperatures favor substitution, higher temperatures favor elimination. (20 degrees, we're going to call low. 50, I've told you guys 50 degrees is the cutoff. I can't remember, does this give a temperature? Good. I used to have a temperature on there. It really does vary. I'm going to say 50 degrees is the cutoff, and I'm not going to give you problems where it's 50 degrees or like 49 or 51. 20, 0, those are low. 100, 150, that's high. So we're going to choose here SN2. All right, if you got it, great. If you thought E2 was the way it was, that's like a second best answer. All right? SN1 and E1 are off because you've got a good nucleophile. Now, if you did get it, just sit tight, you might work the next one. If you didn't get this, draw the SN2 product of these reagents. All right, so in the mechanism, all right, we've got an SCH3. The SN2 mechanism is one step. It's a concerted reaction. The sulfur will attack the carbon with the leaving group. Leaving group gets kicked out. It's a substitution, so the nucleophile is substituting for the leaving group. The other thing is, the SN2 reaction gives inversion of the stereochemistry at the electrophilic carbon. You're only going to see that if the electrophilic carbon is chiral and has one, is either one enantiomer or the other. So the bromide's back. So a backside attack would have the sulfur coming from the front. There's an important feature here. The carbon with the OH is also a chiral carbon, right? The OH is wedged. The inversion refers only to the carbon that gets attacked. Okay, so the sulfur is going to attack the carbon with the bromide, kick the bromide out. Those are the only arrows in the mechanism. Those are the only atoms that are changing. All right, the bonding of the sulfur is changing. The bonding of the electrophilic carbon is changing, and the bonding of the bromide is changing. Everything else is going to stay the same, including the stereochemistry. So this, again, you should understand this feature here that SN2 gives inversion, but you should also memorize it. Ideally, you conceptually understand it. But at a minimum, you need to have it memorized. All right, so that's your product. That's the only product you get. All right, go ahead. I'll give you another couple of minutes to work on the second problem, and then we'll go through the flow chart on that. By the way, you might notice on the first problem, I never talked about the solvent. If you've read the book, maybe, I mean, depending on who you have in lab, solvent does play a minor role in these reactions. Okay, we'll talk about it more here in a bit, but SN2 and E2 tend to be faster in polar aprotic solvents. SN1 and E1 are faster in protic solvents. They are never, the solvent never tells you what the reaction is. Okay, so don't start with the solvent. The flow chart is meant to be worked in order. You can't jump immediately to temperature and solvent and solve the problem. SN2?
SN2, E2, SN1. I'm confused on this one.
Oh, if you're on the fourth one, the last reaction, that lithium methoxide should be in excess. You've got at least two equivalents of it. If they ever let me teach Gen Chem, I will completely botch stoichiometry. Like, how much lithium methoxide is there? Some, I don't know, 2 scoops. Give you another 30 seconds on the second one. All right. So again, flow chart. Do you have a leaving group? Yeah, you got a leaving group. Everybody gets very bored at this. Always make sure you ask yourself this question. Like generally in class, generally speaking, I'm going to put molecules up that do this chemistry, right? But that's not a foregone conclusion. If you don't have a leaving group, chapter 7 stuff doesn't happen. All right, so you got a leaving group. Do we have beta hydrogens? Yep. Do we have a strong base or good nucleophile? Yeah, so potassium hydroxide is a strong base. Hydroxide in general, that's like the first base you learn. And that's sort of, it's almost the weakest of the strong bases in chapter 7. So hydroxide is a strong base, but it's not the strongest base you can have. And then also, like I said, a strong base is something that gives away electrons easily. So if a strong base is physically small, it's also going to be a good nucleophile. The only way a strong base won't be a good nucleophile is if the electrons that are being given away are really heavily protected by like molecular stuff. So hydroxide is both a good nucleophile and a strong base. Saint base. All right, so again, SN2 or E2. SN2 and E2 reactions are driven by the strong base. They don't have to wait for a leaving group to leave. So SN2 and E2 are intrinsically, generally, faster reactions than SN1 and E1. So if SN2 and E2 can happen, that means we have a leaving group, we have a good nucleophile or a strong base. If an SN2 or E2 can happen, that's going to predominate over SN1 and E1. All right, so now, again, you've got beta hydrogens. We've got 2 beta hydrogens here and 1 there. We've got 3 beta hydrogens we can grab. And it's going to matter which one gets grabbed if we do an elimination. So we go left, strong base and good nucleophile. Is the leaving group on a tertiary carbon? Nope, still on a secondary. So we can still do SN2 and E2. pKa of the conjugate acid is, pKa of water is 15.7 or 14 or whatever you want. It's greater than 8. So E2 and SN2 are both possible. Next question is the temperature. Temperature here is hot. So the DMF reaction you guys are running in lab this week is in refluxing DMF. That's really hot. We're doing that to try to make this reaction go as fast as possible. What reaction are you doing in lab this week? What's the reaction type? It's an SN2 at a high temperature. All right, so you can have an SN2 go at a high temperature. The way we get away with this in this reaction this week, there's two things we do. The reaction being done in lab is a relatively weak base. So acetate, the conjugate acid of acetate is acetic acid. So acetate's not a super strong base. It's a pretty good nucleophile, but it's not as strong a base. So that's going to favor SN2 a little bit. The alkyl halide is a primary, right? So that's going to be the fastest SN2 alkyl halide. The other thing we do, and this is a bit of a trick, is the elimination product is 1-hexene. All right, 1-hexene boils at like 65 degrees C, and it's going to come off on the rotovap. So you won't see it. So there's probably some E2 reaction happening in the reaction you're doing in lab this week. The product just goes away. All right, so here, though, the major product is going to come from an E2 reaction. Secondary alkyl halides undergo SN2 relatively slowly because there's a good deal of steric hindrance around the electrophilic carbon. And then a high temperature is going to favor elimination. So now which proton gets grabbed? There are three, well, actually there are 4 possible products. So let's draw these out. So I'm just going to draw these sort of logically. All right, so the double bond is going to be formed between the beta carbon and the alpha carbon. So we can have a double bond here, and we can have a double bond here. And both of those double bonds could be cis or trans, E or Z. All right, so those are the 4 logical possibilities out of this E2 reaction. How many of you drew all 4? Anybody draw all 4? How many of you drew just one of them? That's a fair answer. Depending on the one you drew, you would get a different number of points. So we need to talk for a minute about alkene stability. All right. First rule you should learn about alkenes, and this follows carbocations. Remember, carbocations are sp2. Carbocations are stabilized by substituents that can kick in some electrons by overlapping with that vacant p orbital. So alkenes have p orbitals. Electrons overlapping with that p orbital will help that. So a more substituted alkene tends to be more stable. And if you think about the simplest alkene, that's an ethylene, right? That's ethylene. That's your like base alkene. A substituent is anything that's not an H. Right? So when I say a substituent on an alkene, I mean something that's not an H. So the most substituted an alkene can be is tetrasubstituted. 4 things that aren't H's on there. And then tri. And then a whole bunch of dyes. All right, so you can have a trans disubstituted alkene, you can have a cis disubstituted alkene, or you can have an alkene where the 2 substituents are on the same carbon, and the stability goes as I've shown right there. All right, and then the second thing conjugated alkenes are going to be more stable than non-conjugated alkenes. All right, you guys have already seen this. This is basically cation stability. The more substituted it is, the more stable it is. The more resonance stabilized, the more stable it is. Okay, so a conjugated alkene So the conjugated alkene is on the left, the non-conjugated is on the right. Conjugated alkenes are just 2 alkenes, 2 pi bonds separated by a single sigma bond. We talked about this a little bit in spectroscopy, but again, if an alkene is 2 p orbitals overlapping to make a pi bond, right? So 2 p orbitals separated by 1 sigma bond, that lets the p orbitals overlap. So we've got 2 of these, but we also really have it here, right? There's a p orbital on this carbon and a p orbital on that carbon. They're 1 bond apart, so those 2 p orbitals can overlap. All right, so you can memorize that or you can work it out from first principles. Again, if you know cation stability, you know alkene stability. More substituted, more resonance. Makes an alkene more stable. Okay. And so over here then, rank the stability of these 4 alkenes. All right, so you've got 2 groups here. The top 2 are tri-substituted alkenes. Right? So if we just look at the 4 things coming off the alkene, 1, 2, 3 are not hydrogens. So that's a tri-substituted alkene. On the bottom, these are di-substituted. All right, look at the alkene. 1, 2 things are not hydrogens. So usually the tri-substituted alkenes are going to be more stable than the di-substituted alkenes. We've got a wrinkle here, a little bit of a wrinkle, not much. Up on the top, these 2 tri-substituted alkenes are conjugated. All right, they're conjugated with the pi bonds in the benzene ring. All right, so this pi bond is separated by a single sigma bond from the pi bonds in the benzene ring. The benzene ring, in fact, those 3 double bonds are all conjugated with each other. Again, that's one of the secrets to benzene stability. Down here, these are not conjugated. That's not an abbreviation. All right. Okay, so the 2 alkenes on the bottom, the 2 disubstituted alkenes are not conjugated. So trisubstituted conjugated alkenes are going to be more stable than non-conjugated disubstituted. So the top 2 are going to be more stable than the bottom 2. Are the top 2 the same stability? They're not. So figure out which one is more stable. All right, so now the stability, and I'm only talking about stability, comes down to sterics. On the bottom, I hope you'll see that we've got trans and cis, right? Trans and cis require a rigid structure like an alkene or a ring. And trans and cis have to refer to 2 specific things. So we can only call an alkene trans if there are 2 identical groups trans to one another. And that's going to be the hydrogen. So there's a hydrogen here that's trans to a hydrogen there. So you can call that alkene trans. On the bottom, the 2 H's are cis. So that's a cis alkene. On the top, we have the same thing going on, right? The phenyl is trans to the butyl. The phenyl is cis to the butyl. So there's a cis-trans relationship between these 2 molecules. That makes the 2 molecules diastereomers. But we can't just say one is cis and one is trans. Because, okay, on the top, phenyl is trans to butyl, methyl is cis to butyl. So is it cis or trans? So what we do here is E and Z. This goes back, remember what we did with R and S? So we do E and Z the same way. So on this carbon, we're going to assign priority to the 2 things coming off by atomic weight. Okay, so we have carbons coming off that sp2 carbon. Carbon, carbon, that's 3 H's, this is 3 C's, right? So this is going to be 1 and 2. So 1 is the highest priority, 2 is the lowest priority. On the second carbon, on the other alkene carbon, carbon versus hydrogen. So carbon is 1, hydrogen is 2, right? So assign your priorities. And that's going to make this an E double bond. So the ones, I need a place to write. If the high priority groups are trans to one another, it's an E double bond. That comes from a German word, entgegen. For anybody that speaks German. On the bottom, so again, we have 1 and 2. But now the 1 group is cis to the 1, right? So carbon versus hydrogen, the 1s are cis. That is going to be a Z double bond, which is, I forget, zusammen, I think. It's like together, I think. I have a very little bit. I know many of you are probably frustrated with Wake Forest foreign language requirement. I hear this from advisees a lot. Lean into it, man. Like, I went to Oklahoma State. They did not care about foreign languages. I had to take, the chemistry department made me take a year of German at the time because before the Second World War, the Germans and the English sort of dominated chemistry. All right? And so there is an awful lot of chemical literature and a lot of chemical discoveries that were made and reported in German. was felt that you needed to be able to read German to do chemistry. So I have like these little snippets of German, and really all it did is made me unable to pronounce an English W for like 20 years. All right? You're a better person if you can speak more languages. Okay, so E and Z. E corresponds to trans, Z corresponds to cis. Like this. That's how I remember it. Very sophisticated memorization technique. Okay, which one is more stable, the E or the Z in this case? E is. That is not always going to be true, all right? Trans is always more stable than cis. We have this big group here, we have a big group there, and we get them as far apart as we can. It's why the anti-conformations back in Newman projections, why those are more stable. Having two big groups gouge to one another is destabilizing. So here, having two big groups cis to one another is destabilizing. So the trans, on the di-substituted, the trans isomer is more stable than the cis. On the top, we have the big group phenyl trans to the big group butyl. Here, we're talking about steric bulk, not atomic weight. So it won't always work out that the priority 1 group being trans makes it the most stable. Often it will, but you're looking at getting the two sterically largest things farther apart. So in terms of stability, 1, 2, 3, and 4. The top one is the most stable alkene that we can get out of this reaction. But that is not how we know what the product is. All right, so I'm leaning in, I'm chewing up valuable time. Figure out, let me just tell you this. Like, we probably will get a little bit of 3 and 4. All right, we'll get a little bit of the di-substituted, both cis and trans. We'll get more of the trans, less of the cis. On the top, we can only get one of those. So I'll give you a couple of minutes to figure out which. Actually, let's not do that. I'll work through it. Sound good? Does anybody have a guess? I want you all to make a guess. Okay, you don't have to tell me that, but you can. I appreciate that. All right, if you say the top, are you saying it because it's the most stable? Yeah. All right, most stable doesn't matter here. We're going to get the alkene that results from the abstraction of an antiproton here. I don't mean that like subatomic particles. The H in the leaving group have to be anticoplanar for this reaction to work. So you're going to like this, I promise. You know how to do this. We're going to draw a Newman projection looking at down the bond that's going to become the carbon-carbon double bond. No, you all love Newmans. I know this. My Yelp reviews, everybody says they love Newman projections. Now you're wondering if I really have Yelp reviews. I don't think I do. All right, let's draw the Newman just as it's drawn here. Okay, so front carbon is here. I've got a methyl up to the left. I've got a phenyl down. So a benzene ring is called a phenyl group, PHENYL, and I've got an H here. That H is the proton that is going to get grabbed to make the double bond. The back carbon, I've got a bromine down to the left. Right? Bromine and methyl are both dashed, so they have to be on the same side of the Newman. I've got an H coming out at us. I've got a butyl group going back. All right, so that's the Newman projection of the way I've drawn it. Now, can the E2 elimination happen from this conformation? Yeah, it can. All right, so when I say that the beta proton and the leaving group must be anti to one another, that's what I mean. As you draw the Newman projection, they have to be directly opposed to each other. Just like in the SN2, you get an inversion of configuration at the electrophilic carbon. That's a stereochemical requirement. All right, so the SN2 is going to give, it's going to give you one. If I start with one enantiomer, I'm going to get one enantiomer. In the E2, I can only get elimination when I have a beta proton anti to the leaving group. And now, what does this mean? Well, what this means is, since it's a one-step reaction, okay, so hydroxide is going to grab that proton, make the pi bond, kick out the leaving group, all in a single step. There's no time for this to rotate around. Okay, so if in this conformation the phenyl is on the same side as H, right, so the phenyl's gouged to the H, it's on the same side of this anti-periplanar line, then in the alkene, the phenyl and the H have to be on the same side. Right, this thing just kind of collapses down like a pancake. Whatever's on one side stays on one side. Whatever's on the other side stays on that side. So that is going to correspond to, you got it right. All right, that corresponds to that alkene, right? The phenyl group, this benzene, is cis to the proton. The butyl group is cis to the methyl. Butyl is cis to methyl. We don't see any of that second one. Yeah.
So you can just use like this drawing of the first one to map out the second one?
Well, yeah. So you can, I mean, this, if you drew this as the mechanism, this would be fine. If you can see the H being anti to the leaving group without drawing a Newman projection, that's also fine. I think for most of you, the fastest way to the correct answer is to do a Newman projection. I mean, I know, jokes aside, that seems like another step. It seems like a step you're maybe not all that confident in. But trying to do this in your head is going to be really hard. Obviously, if you get down like on exam 3, this is the last problem on there, and I've said you got 10 seconds. Okay, you're not going to be able to do a Newman projection. If you haven't seen it, it's 50-50 at that point, right? Circle one of them. Point is, in an E2 elimination, you cannot get an alkene that results from a proton that isn't anti to the leaving group being abstracted. It's only for E2. Now for E1, right? So if let's say we don't have KOH, right? We don't have a strong base. We don't have a good nucleophile. So now it's SN1 or E1. It's 110 degrees, so we're going to do E1. Now E1, the leaving group leaves. We get a planar carbocation. Now we have no stereochemical requirements for that elimination. For E1, you'd get all 4 of these. What else do I want to say about that? For E1, the reaction goes backwards. Right? E1 is an equilibration process. You're going to have acid. Here, the E2 does not go backwards. Hydroxide grabs an H, that makes water. Right? If I have an alkene and water and no acid, nothing happens. So the E2 and the SN2 are one direction. Irreversible reactions. E1 and SN1 reverse. Okay, so again, just the take-home message here is in the E2, your beta proton and the leaving group have to be anti to one another. All right, so on the third one, what's the mechanism? It is an SN1. Anything weird happen? So what kind of is primary, secondary, tertiary bromide? Secondary. Is the product a halide or an alcohol? It's an alcohol. Primary, secondary, or tertiary? It's tertiary. So there's a cation rearrangement in there. We might come back to that one. I want to get to the fourth one, and then I want to do a couple of the rate equations. So I'm going to draw the fourth one up on the board. Take a minute and look at that, and then we'll look at, come on. Oh, you know, something I wanted to interject here. I meant to make this point. I did this on purpose. It's probably not. On the very first one, I wrote the reagents over the arrow in a different order. All right, the stuff over the arrow, there's no place of importance to what's on top of the arrow or below the arrow or where the temperature is. It's all just information. Basically, it's saying this compound is treated with all of this stuff at whatever conditions are listed here. The only way that's different, occasionally, and sometimes this is important, you've seen it a little bit. There were a couple of reactions in chapter 8 like this. Sometimes occasionally on the reaction arrow, you'll see us write 1 stuff, 2 stuff. This is different than that. All right? The second one, there's no 1 and 2. It just means X, Y, and Z, and A, B, and C were all in there at the same time. On the left hand one, it means first we treat whatever's over here with X, Y, and Z, and then whatever results from that, then we treat that with A, B, and C. Okay? So don't get hung up on what's on top, what's on bottom. This stuff can go in any order. Okay. So, flow chart. Leaving groups present, right? I got very enamored of bromides on this one. So we got bromides, we got leaving groups. Are there beta hydrogens? For all of them? For both bromides, are there beta hydrogens? Yeah, there are. All right. So here, the trick to this one is, right, we got this bromide, we got that bromide. Well, which one's going to react? And the answer is they both react. They're both leaving groups. All right, so we got beta hydrogens, we can do elimination. Now, is there either a strong base or a good nucleophile? There is. Methoxide is a strong base. Again, this is going to be lithium plus O minus. That's a localized O minus like hydroxide. So methoxide and hydroxide are really closely, they have very similar base strengths. So if hydroxide's strong, methoxide's strong. Methoxide's a little bit bigger than hydroxide, but really not much. It's got a little methyl group. Methyl's bigger than a hydrogen, but it kind of gets out of the way. Stick the electrons out front, push the methyl to the back. So this is both a good nucleophile and a strong base. So we go left, we're going to do either SN2 or E2. And you might notice this is in a polar protic solvent. You can still do E2 and SN2 in a polar protic solvent. I really will. I will talk more about solvent here in a minute. Is the leaving group on a tertiary carbon? Okay, again, this is like, you know, I got dealt 2 4s in blackjack. All right, I've got to separate them now. So that might not have been the best analogy in the world. We got to treat the bromide, the tertiary bromide, we're going to treat as its own problem. We essentially now have 2 problems, is what I'm saying. We got a tertiary bromide, we got a primary bromide. Tertiary bromide and a primary bromide. All right? Primary bromides do pretty well in SN2. They're not very sterically hindered. Tertiary bromides are so sterically hindered they cannot do SN2. So here, all right, so on the tertiary bromide, we can't do SN2. On the primary bromide, we can do E2 or SN2. So we go both ways. We go yes and no. And then on no, what's the pKa of the conjugate acid? pKa of methanol is 16. So that's a really strong base again. So again, we can do SN2 or E2 there. We're going to come down to temperature. Right? And so now the answer to this problem is going to be that the tertiary bromide does E2, the primary bromide is going to do SN2. Nope. All right, and so in terms of, there's 2 beta hydrogens on this carbon, right? We're going to end up with, we have a choice of a disubstituted or a trisubstituted alkene. The major product's going to be the tri. We've got 2 bromides there. We could get E or Z. Having the 2 big groups trans to each other is going to be the major product. If you drew this one with the diastereomer, if you had this group cis to the phenyl, I'd probably be okay with that. Certainly wouldn't be a big deduction if you said that's an E2 and the other one's an SN2. There's no stereochemistry on this carbon. It's still a backside attack, but there's no way to see that in the product, right? Okay. So I'm going to draw the product. Go ahead and start working the reaction rate problems if you haven't already, number 2. And I'll come back to that first one here in just a second. I'm going to draw the third reaction over here on the left, and I'll leave that as an exercise for you to work out. All right. On the left board, that's the third reaction. I'm going to leave you with just a little bit of homework. It's an SN1 reaction. All right, you got a leaving group, you got beta hydrogens. It's a secondary halide. There's no good nucleophile or strong base. Water is a weak base, weak nucleophile. All right, neutral oxygens are not going to be strong bases. So not having a good nucleophile or a strong base takes you to the SN1E1 side of things. From there, the temperature is mostly going to determine what happens, all right? It's a low temperature, so we're going to favor SN1. Leaving group's going to leave. We're going to get a secondary cation. Stuff will happen. We wind up with a hydroxide bonded to a carbon, all right? So if you want to know how that hydroxide ends up there, you have to draw the mechanism for the reaction. I'll put this on the key that I'll upload later today, but try to work out what the mechanism is first. All right, so here, this is number 2. We're starting number 2 here. So what kind of reaction is this? It's an E2. All right. You know it's an elimination. You lose the leaving group, and you get an alkene. So that's going to be an elimination. How do you know it's E2, not E1? There is a strong base. T-butoxide, again, a localized negative charge on that oxygen. Tert-butyl group, so it's fairly sterically hindered. T-butoxide is a really good base. It's a really strong base. Sterically hindered, it's not a great nucleophile. So even at 20 degrees, like, you might look at that. If I'd asked you to predict the product, you might have said SN2 because the temperature's low. Doesn't matter here. I've given you the product, all right? Anytime I give you guys a product, don't like reinvent it. If I say we have this reagent, or if we have this starting material and these reagents and you get this product, I'm going to ask you questions about how that happened. Do that. Don't say, no, 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 Dr. Jones, something else happened. All right, so it's an elimination reaction. It's an E2 reaction. So which one is faster? How come? It's at the same temperature, though, right? You're right. The bottom one's faster. Right. So this is the solvent difference, and I promised you I would talk about this. So if you think about this reaction, I'm going to redraw this so that the leaving group is anti to the beta proton. All right. This reaction is driven by the base grabbing the proton. All right, so the T-butoxide giving electrons away is what drives this reaction. E2 and SN2, that's the case, right? The base or the nucleophile is driving the reaction. So in methanol, all right, you have a lot more methanols than this, right? You've got hundreds, thousands of methanols for every T-butoxide. But that T-butoxide, that O minus, can hydrogen bond to the OH in the solvent. So when we say a protic solvent, we don't mean a solvent that's got protons in it. Because DMF has protons in it. Again, let me draw the structure of DMF. DMF has 7 hydrogens in it, and yet we call it an aprotic solvent. That doesn't really make a lot of sense. Actually, it makes no sense. It's terrible use of language. All right? Scientists did this, probably some Germans, I don't know. Russians, they were Europeans, let's say. All right, so the language is bad. We call this an aprotic solvent. What we mean is DMF has no H-bond donor. DMF actually is a really good H-bond acceptor. All right, if you put DMF in water, it hydrogen bonds to water really fierce. But it doesn't have a hydrogen that can donate a hydrogen bond. Okay, so on the left, and I've drawn all these, like this hydrogen bonds form really fleeting. and this is probably, you probably don't have to think about all this in working out the reaction. A hydrogen bond is not terribly strong, all right? It's not like a covalent bond. It forms and breaks hundreds of millions of times a second. But there's so much methanol floating around, right? If it breaks here, then it forms there, then it forms over here. It's always hydrogen bonded. That ties these electrons up. The t-butoxide, to drive the reaction, is trying to give the electrons away. Right? I want to donate to the Juvenile Diabetes Foundation. I'm diabetic. I don't know if I mentioned that. Like, everybody should donate to them. Kidding. You don't have to. I'm not allowed to do that. They don't have to donate to anyone. All right. But let's say I want to donate a lot of money to diabetes research. All right. The bank comes and wants a mortgage payment, car payment, city makes me pay for water. Right? All these things are like taking money away from what's important, which is diabetes research. So here, the electrons are, the t-butoxide to drive the reaction needs to give the electrons to the beta hydrogen. Can't do that though, because all these other things are demanding the electrons. Meanwhile, in DMF, right? There's no interaction there. That O- isn't interacting with the DMF at all. So those electrons are now free and clear to go to the beta hydrogen. So this is the faster reaction. SN2 and E2 are not more, they're faster. The reaction does need to be done in a polar. The reaction's polar. We got to have ions and electron transfer. That's going to be faster in a polar solvent. Okay, so, but we want to have it not be a hydrogen bonding polar solvent. So DMF, acetone, DMSO, there's a whole bunch of these. You don't have to memorize them. I'll give you the structure. If I ask a question like this, you'll get the structure of the solvent. Okay, so SN2 and E2, because they're being driven by the nucleophile or the base giving electrons away, are slower in a solvent where those electrons are hydrogen bonding to something. It's the reverse in an SN1 and E1 reaction. Right? In an E1 or SN1, let's look over here. Okay? So the first step here is the leaving group leaves, and we get a cation. That's the slow step. If you speed up the slow step, you speed up the reaction. And now, we're in water. Right? So that bromide can hydrogen bond to the water and be stabilized. The hydrogen bond donating ability of the solvent stabilizes the Br. That makes it leave easier, makes the reaction faster. So SN1 and E1 are faster in polar protic solvents. Okay, that's probably enough for today since time's up. There's 3 more rate reaction ones to run or to work. There's the mechanism for the third one here, and then there's a mechanism at the bottom that's kind of related. I said I would put a key up for this. I tell you what I'm going to do. I'm going to put this up blank, and then I'm going to finish all these in class on Thursday. So if you're not in class on Thursday, watch the video, and I'll put a key up for this after class on Thursday. All right, so I'll see some of you in lab here in a minute. Enjoy your SN2 reaction if you're doing that in lab this week. Yeah, good luck with this stuff. Oh, there will be a Chapter 7 quiz at some point in the next few days. It'll probably go up, and you'll have 2 or 3, 4 days to work it. All right? See ya.
Pertaining to, you mentioned you can't take the lab before the lecture for 223.
Right.
I am enrolled for taking the lab in the summer because I couldn't get the lecture because it filled and I never got. I was unable to apply for the lecture.
They will eventually catch that. You need to talk to somebody.
Okay.
Yep, see ya. I mean, I'm sorry to tell you that, but like somebody will eventually catch that you're in.
Yeah. So they let me. I tried enrolling and it said you can't enroll
In the lecture.
in the lecture, but it did let me do the lecture. And then
Why?
I
Like
contacted
it's
them.
full? Is that?
Sorry?
Is it full? Is that what the deal is?
Now it's full. It wouldn't let me before.
You need to talk to somebody in the registrar's
So I
office.
also can't. So I don't. Yeah. I'm.
Like rather than do half the lab and then be told, nope, you can't do it.
Yeah.
Like, yeah. So yeah, talk to somebody in the registrar or the department. All right. Yep.
For study abroad, so like there was like one in London. Who's the best person to contact?
Krista Collier is doing the study abroad in London.
You know that if it's actually going to happen with everything going on here?
The spring of 22, I'm really confident that's going to happen. I think most of them will go in the fall. So yeah, you bet.
How are we supposed to know the pK of a conjugated acid if it's not on that chart that you
Yeah, that's a good question. So you have to know the ones on the chart.
Yeah.
The sulfur one, like I gave you a list, gave the class a list of molecules that are better nucleophiles than bases. So that would be enough for you to steer that one toward nucleophile. If it's something else, I'll give it to you on the test. Yep.
Other question was, you mentioned that the final being optional, you just take the grade average.
Right.
Other exam, so it would have basically no effect, right?
Well, I mean, so whatever your midterm average is, like the average score on the 3 exams, that would be your final exam score.
Yes. And then you mentioned there would be a term that wouldn't be that severe, but would that play into the final exam grade at all?
I mean, it won't. No, not the final exam grade. But if the average, I mean, this has never happened. But like, if you took your midterm average and then the average score on the final was 98, probably hurt you relative to everybody else. I wouldn't bank on the final exam score being 98. So, and we can talk about that a lot more when we have some scores. Yeah. You bet. See ya. Oh, I'm still recording.